Today is a rare occasion where I can actually speak for a while, so I guess let's make the most of it, not waste too much time on irrelevant stuff. So today I was thinking of doing a Leetcode problem. I lost my old account. I think I'd probably find it somewhere if I really wanted to, but it wasn't a rated account. I only had like 50 problems solved, so let's just do. Anyways, I like this problem, and I don't think I ever managed to actually solve it, so let's do that now. And yeah, back when I did Leetcode, I did like 50 problems, and I never actually used C++ for it. Anyways, yeah, I think this is fine. Void solve. I'm just gonna do like a basic thing, so yeah, there's only one test case. I'm just doing this so I can like test my solution. Probably should have included readback stuff, it doesn't matter too much. These are guaranteed. They could be negative too, so I guess. Yeah, let's just do. Pretty sure what I can do is just put this above, just make this thing, like, I'm pretty sure this will compile, and then, I'll just do return 0.0 for now, and let's make this all tabs. Didn't work. That's annoying. Then cat solution. Does this work? No, it doesn't. doing this stuff when I should be focusing on the problem, but maybe if I just do does this work? How about this? Oh, I should be like they say. Yep. Anyways, now let's actually get on to doing the problem. So I've been thinking about this problem before. I think the way I will do it is just recursively narrow the search space. So what we'll have is we'll have lower bounds for lower and upper bounds for numbers 1 and lower and upper bounds for numbers 2. And inclusive, exclusive, so like the canoe, I think it was. So, well, we have that, and then we want to know their values in the combined array. So we'll define indices in the combined array. I just wrote some stuff out. We'll probably want to have like the true lower bound of this is hard actually. So we have 2 arrays. Yeah, we'll be repeatedly like. Actually, might not even need to do that. We just track deleted from above and deleted from below. I think it should work. Deleted from above, from below, deleted from above. And DL and DU. I'll just keep it there so it actually compiles. And these will be initialized at that. To -1 dot size. And that will be initialized to -2 dot size. These will just be that. So the main loop will be while let's just find the combined size of the array. So combined size equals -1 to its size. We want to continue until deleted from let's consider first the case where you have an even. If it's an even, we want to have 2 in the middle, so we'll delete 1 from each side. If it's an odd, we want to have 1 in the middle, so yep. So what we can do is we can add 1 to the combined size. Or rather, it might just be easiest to subtract 1 from the combined size. So in that case, 4 would go to 3, and 3 would go to 2. And then we divide that by 2 using integer divide. So I think that works. So that's combined size -1 over 2. So those. It's probably just easiest to find like what is the largest. So if we have 2 segments, the midpoints of each segment would it just be easier to find like I think it But the question is, would that be O log n squared? No, if you just find the midpoints of each one. Then there should be scenarios where we get to discard large slots. Now, let me think about this more carefully. L, R. So there's 4 segments in that scenario that we can... The ones that we're looking at eliminating are yeah, I think it'd just be easier to like try to find kth elements. I'm thinking about this a while. Yeah, just find the max of and then, yeah, once you find like the kth elements in one array. Oh shit. Oh, let's make this like this. You can find its position in the other. Once you find the midpoint of one, use binary search to find the midpoint, to find that location in the other array. Then delete accordingly. Should work. I'll just have to worry about like the specific locations of indices and stuff like that. So Yeah, I think we'll just call it this. While L3 is less than R3. L3 equals L2. Yeah, I'm just thinking about this the wrong way, so we'll just... Or I use this convention, so let's just do this. L equals M equals L plus R slash 2. So the value is, we just set otherwise, and we increase that by 1. So this should give us the index of the value in the second array. And it should be the index just above. I think it's just above. Not exactly sure. 0, 5, 2. So it should be this. Wait, what am I thinking about? This is correct. Yeah, it gives you the one right above the index. So in this scenario, we have these 4 arrays, and we know that all elements of the left array are lower than that, and all elements of the right array are lower than that. So this is a special case because there's only 6. So. In this case, the 6 is taken away from both. Sorry for the construction going outside. Yeah, and if well, that makes it easier. Just find the kth elements. Okay. Yeah, this is not going to be fun, so what I'll do is I'll comment all this out, and then we can copy stuff as needed. we have 1 and 3, like 1 and 2, so in that case there's 3, just 1. And this will be 0 index as well, so we'll just, divide by 2. And if it's like that, so in that case we have 4, so I'm just choosing any even numbers, thanks. Divide the size by 2 and divide the size by 2 minus 1. The first thing we can do is that, we want to have like lower enough for bands too. We'll just do that with the helper function. This is getting very complicated. What we'll do immediately is lower some bounds. So if we know that it's the kth elements, if we know that 0, we can. What I mean is, if you know that k is, we can like trim nums 1 and nums 2. Because there's only going to be like so many. X is what's it called? Zero indexed. K is zero indexed too, which makes it a bit of a pain. So, like if we have an array here, K equals 4. So we want R minus L. If R minus L is greater than K plus 1, R minus L is greater than K plus 1, we'll add K plus 1 to that. Zero. Yeah, I wonder why is this so slow actually. Then I forget to because it's like compile it classes as well, which makes it annoying. And we'll do the same thing for the case too. Now we finally get to begin the fun stuff. Oh yeah, we want to consider cases where L1 equals R1 and L2 equals R1. Because in these cases, it's just empty. In fact, what we can do is it probably will not matter, but this is a tiny bit safer. So yeah, what we'll do now is we'll choose the midpoint in those ones. So we'll call that int m1. M1 equals L1 plus R1 divided by 2. Then we'll binary search for that inside of that. So define L as being L2, R as being R2, and M is just a placeholder. So what we'll do is while L is less than R, M equals L plus R. It's just standard binary search. I think it's the same stuff we did above. I don't need any of this stuff anymore. I'll just set t equals just 1. If it's less than t, otherwise r equals that. I think this should work. And then I'll just do some basic tests to see how this. Let's consider that accidentally calculated that wrong. Doesn't matter too much anyways. Yeah, I think this binary search should work. Anyways, now we have 2 values. And M should point to Gek. I think it's levels 2 and it should be greater than or equal to. Then we can just like turn off stuff. So there's 2 cases we have to consider. There's M1 minus L1. If M1 minus L1 plus M2 plus, no, we used M, so M minus L2. If that's less than K, then we search within that. otherwise you search within the other section. I think this should work. Okay. Good. The things are obviously a bit tricky. And in this case, we want to subtract M1, and that's from the thing. So we do M1, there's 2, M minus 2, we'll do K minus M1 minus M1 minus 2M minus. And I'm fairly sure that this solution should work. So this one's supposed to return the index there, so I think it should work. Don't worry about it too much. Where does it reach the end of it should not do that. Wait, no. And let's see what the cases are. So. Oh yeah, we always just want to test for the case where there's only one of each.